And we should be live right now, everybody. Hello, I see people coming in. We have the attendees number growing fast, so I'm going to give it a couple of minutes for everybody to feel the setting, to see the picture, make sure they hear us, they see us, so we can start with today's session. My name is Milana, and I'm the community manager of WeAreDevelopers and the host of the WeAreDevelopers live sessions. Very happy to have you all here and to have actually Marta joining us today. As we are starting, I'm gonna ask you all to introduce yourself in the comments. Give us some feedback. Tell us hi. Tell us where you're coming from, where you're watching us actually from. Because this live streaming, it's really weird for the presenter because you don't hear any feedback, you don't see any faces. So your comments are very, very appreciated. So please give us some thumbs up or just say hi. I am in Berlin, I am in Madrid, wherever you are, just tell us so we can show that there is some communication going on here. And with this being said, I'm gonna start introducing you to WeAreDevelopers and to the session today. And as this is a public event and everybody can watch and you can write freely in the comment sections on the right side, I'm just going to ask you to stay kind to one another and to respect each other in the comment section, because our online events also comply with our physical code of conduct. So that's very important for us. So keep the good tone. And yeah, feel free to ask questions as well. Where you see the chat, right there next to the chat icon, there is a small question mark. And if you click it, you'll be writing a question. We will not be reading the questions throughout the presentation, but only at the end, after Marta tell us all about stream processing with Apache. And I think I'm super excited to have this session today because I have changed the setting. If somebody has watched us before, you can see that I am currently in our office preparing for our WeAreDevelopers Live Week. What is WeAreDevelopers Live Week? Next week, we're going to have a full week of online sessions from Monday to Friday in memory of our postponed conference. So we're going to have all day talks, and I'll give a bit more information about it at the end of this presentation. And now, not to actually have you waiting on the topic, I'm going to introduce it to Marta. Marta is a developer advocate at Ververica, very nice, very long-term partner of WeAreDevelopers. And we are very happy to host this together. She is also a contributor to Apache Flink and has a master's degree in biomedical engineering, which like thumbs up for this. And with her experience, previous experience also in Zalando, Unit4 or Accenture, I'm sure she has a lot of knowledge to share with us today. And with this, I'm gonna turn off my camera, my mic as always, and give the spotlight to Marta. So keep writing comments throughout the presentation, give her feedback and ask questions so we can have this conversation going.
Okay, thank you so much, Liliana. Also, thank you for having me today. And hi to everyone on the other side. I'm really glad that you took the time to come to this presentation today. My name is Marta. I work as a developer advocate at Ververica. And today I'm going to tell you a little bit about stream processing and Apache Flink. And my goal with this presentation today is not really to go super deep into the nitty-gritty of Flink. I kind of wanted to make something that is a bit more accessible and a bit more like an overview that you can easily understand if you're irrelevant of what background you have. So if you're a data scientist, a data analyst, data engineer, if you're a product manager, anything, you should be able to follow along. And if you don't, please just give me feedback after the talk, and let me know if you learned something new. Okay. So to start, just a little bit about Ververica. It's the company that was founded by the original creators of Apache Flink. This means that I am really privileged to every day work very closely with some of the core maintainers of Flink. And I also have the privilege of being really involved in the Flink community, which is amazing. What Faverica offers is enterprise-ready distribution of Flink, so that is called Faverica Platform. And since 2019, we are part of the Alibaba group. So I don't really know what the background of the people attending this today is, but because WeAreDevelopers is like a really broad conference, I'm just going to start with a quick recap that introduces you to stream processing if you're not familiar with it at all. So if you've been at least working with data for some time, maybe this scenario that I'm presenting here will ring a bell to you. So not that long ago, this is what analytics used to look like. You had a bunch of transactional databases and maybe some static sources of data. You would run like these really intensive ETL processes to really integrate all this data and combine it into something that is useful for you and for the business that you are serving. And you would store this data in a data warehouse in like nicely structured tables that serve some business purpose. And if you're lucky or are already in a really advanced stage, maybe you already have something like a data lake that you are using instead of this kind of setup. So the quest for data in this kind of setting is something like this. So you would run some very long nightly jobs, and after some time, you would get your results. And unfortunately, in reality, this isn't really what happens, right? You have your long nightly jobs. One or more of those nightly jobs will likely fail at some point, either because your processes just exhausted memory, or because someone decided to use single quotes instead of double quotes in their Excel spreadsheet. And then someone would have to wake up, that was me a lot of times, fix the problem, and then restart these really long nightly jobs. And in the morning, you would have someone complaining, usually a stakeholder, because they don't have their data and their data is late. And after all this painful process, you would finally deliver your results to whoever needs them. But in the end, if you really look at it, like most of your sources of data are producing data continuously. And so it doesn't make sense that someone is waiting for yesterday's data, and then on top of that, your data is still even later, just because something failed. And also, something that you can observe is that most logic is the logic that you use to process all this data actually doesn't change that often. Like it maybe changes if you have a new business requirement or if you have a bug or something like that. But what's really changing in this whole scenario is your data. And this is kind of the transition to today, right? Something we can't really escape now is that everything is a stream. So what used to be in the previous scenario, what used to be like your static data records become like dynamic events that are continuously being produced and that should be equally continuously processed. So what you have now in comparison to what I showed before is something like you have a set of event sources that can really be anything. They can be like connected devices and vehicles, application logs, web clicks, financial transactions, just things that are constantly all the time producing massive amounts of data. And what usually happens now is that you kind of ingest all of this data into a distributed, centralized place using some kind of a message bus or a log like Apache Kafka or Kinesis or Pulsar. And this is kind of the source of truth now for your organization. And over the sequence of events that are produced and that you are ingesting, you might want to run like a set of transformations and computations. So you maybe want to filter out some bad data, you want to correlate events, maybe you want to calculate some aggregations over time. In the meantime, maybe you want to persist some intermediate results that you have from all these computations. You want to put it out or put it aside on a long-term storage, something like a distributed file system like HDFS or S3. And then you publish your output to some sink. And like the sources, your sinks nowadays can be anything, right? You can be triggering an application, you can be producing more event streams to another log. You can be doing updates on databases, so anything. And now the time that it takes from your data to go from your event sources to your sinks might be more or less critical, depending on your particular use case. But you certainly don't want to have like a full day or more of lag between when your data is produced and when you can actually derive the insights from that data. So in very simple terms, everything that happens in between your sources and your sinks is stream processing. It's just like continuous processing of unbounded streams of events. And ideally, you want to have very fine-grained control over this processing. So you kind of want to be able to process these events one at a time. And in the simplest terms, this is what you have. You have an unbounded data set of incoming events that is called a data stream. You have your code, and within this code, you want to do some transformations or do some computations on this incoming data so that you can output the result of that downstream somewhere. And things start getting a bit more interesting and a bit more challenging when you add this concept of memory to this very simple model. So the idea is the same as before. You have data flowing in, you have your code performing computations, you have your data flowing out, but now your code or your application is able to remember the event that it's processing. So you can imagine something like a counter. You can maybe just count the number of events that you are processing every minute, and you have to be able to persist this count and increment this count somewhere. And this usually is your state. And the real challenge with doing stateful stream processing is that it's not really enough that it's this model that allows you to remember things and affect computations based on events that you already saw. It goes a bit beyond that. It's you not only have to be able to maintain state, you also have to be able to manage it in a distributed setting, so like across multiple machines. And you also want to make sure that if something horrible happens, so like if your application just goes to shambles, this state doesn't just vanish and leave you with nothing, with an empty state of the world. So what is Flink, or what is Apache Flink? Flink is an open source framework that allows you to do exactly this. So stateful stream processing. It kind of goes in the same direction that I talked before. So you have events that are continuously flowing in. You consume them. You apply some stateful computations over these data streams. You build some context or some state of what you have seen go through the system, and then you output your results somewhere. And if you just remember one thing from this presentation, I hope it is the word stateful, because this is really what makes Flink, what sets Flink apart from other stream processors. Like state management is really what Flink does well and what makes Flink very powerful. And this is also combined with the fact that Flink is very flexible because it is a true streaming engine. So you can really process events one at a time, and you can also consistently process these events even in the event of failure. So this gives you a very robust foundation, because it's such a simple paradigm in theory that it gives you a really robust foundation for a wide range of use cases. So you have something like, for Flink users, we usually see three different categories of use cases that they are using Flink for. So the first category is really stateful stream processing, in the sense of really classical core stream processing use cases that build on primitives like streams, events, state, and time. And what these use cases take advantage of is really having fine-grained control over the events, and using this to perform some complex computation and maybe like really customize your code, and with the ultimate goal of maximizing the performance and reliability of the system that you build. So some examples of these use cases are using Flink to build core infrastructure. Like, you just use it to build really large-scale data pipelines. One example is Netflix. They have like their backbone of data processing. It's a platform called Keystone, and it's based on Flink. They are processing something like 3 trillion events, I think, per day. Another use case is just building fraud detection engines, where it's really, really important that you have very fine control over things like time, because you really want your events to be processed with really low latency, but also you want your events to be highly correct. And a third use case is using Flink to do like massive log analysis, to do something like service monitoring and anomaly detection. And this is a use case that I always find funny, because AWS is using Flink to monitor their managed Kafka service, which I find funny. And on a different spectrum, you can also use, or you also have users using Flink for streaming analytics and machine learning kind of use cases. So these are more high-level or domain-specific use cases that can be modeled with SQL or Python, and can really be based on something that is a bit more intuitive, like this concept of dynamic tables that are constantly updated. And here, unlike in the previous case, like, you're not so much focused on implementation. You really want to focus on your business logic and implementing something that is adequate to your business requirements. And you kind of want things like state handling or optimization to be handled transparently, and it's not your problem. And Flink just takes care of that. And these are also use cases where maybe you have mixed workloads. So like, if you want to backfill historic data before you start a pipeline that is processing real-time data, Flink also supports both batch and stream processing. So you can also do that. And here, like, your focus, or if you're using Flink for this kind of use cases, really what you want is to maximize developer speed and autonomy. So you really want people to become really independent with their data needs. And a lot of these use cases kind of build on the previous one, because what you have is a lot of companies like Uber or Lyft or Yelp that build self-service platforms that they deploy organization-wide, and then they allow users to use these more high-level abstractions to really build themselves end-to-end streaming analytics pipelines, or something like building and maintaining materialized views, or for machine learning workflows. Maybe you really want users to be able to do things like own their own feature generation pipeline. You don't want them to depend on some engineering team. And the last category I'm going to gloss over a little bit because this is a bit of a new field, at least in the way that we understand it now. It's a bit more of a new field for Flink. It's event-driven applications, but it's in the sense of use cases that really go beyond stream processing, but that can still really use this very powerful primitive in Flink, which is state management. So this is something that extends into a new field that is called stateful serverless applications. So if you want to check it out, I dropped some links here, and it's really interesting and it's very promising kind of use case. But I think it's a bit too much or a bit too complex to really go into it in like an introduction to Flink. So with this wide range of use cases, Flink really powers some of the largest companies in the world, and it serves so many different industry verticals. You have a lot of people from mobility using Flink, entertainment, e-commerce. You even have the TikTok guys using Flink, which is pretty cool. And just to give you an idea from here of the scale at which that Flink can go to. The biggest production installation that we know of, at least until now, is what Alibaba is doing in this huge annual shopping festival called 11 or Singles Day. Maybe you know it also from the giant dashboard that is all over the media in the days following it. And on this particular day, Flink is backing almost all real-time data applications that Alibaba is running, things like search and recommendation, all their advertisement, business intelligence, security apps. And Flink is also behind the updates to the GMV dashboard. And the scale that they are running it is really unlike anything we really see elsewhere in production. They are running Flink on over 5,000 nodes with more than 500,000 CPU cores. And at peak, they are able to process 2.5 billion events per second, which is pretty impressive. And their biggest job is handling 100 terabytes of state. And all of this is done with sub-second latency. So this really gives you an idea of the limits of Flink or how much you can push Flink. But this doesn't really mean that you can only use Flink for these huge use cases. You can actually also go pretty small. So in one of our conferences last year, we had these guys from UHopper, and they built a platform for developing and deploying fog applications in resource-constrained devices. And they managed to deploy a Flink application on a cluster of 5 Raspberry Pis. And so basically they called it the fridge. And basically what they were doing was consuming traffic information from connected devices, and then they were outputting some aggregation. And they were able to process 800 events per second easily without even exhausting the resources of their little Raspberry Pi cluster. I'll have to link to the article if you want to read more about it. I think it's a really interesting use case. And yeah, you can just use your laptop and fire up an IDE and build and debug your Flink application like any Java or any Python application. Okay, now that we're done with the context and really what people are using Flink for, I would like to go a bit into what makes this possible under the hood. So what really makes Flink Flink and what really makes Flink different? It's basically a combination of these 4 different things on how it is designed. So it provides you a set of very flexible APIs. it is able to do what we have been talking until now. So stateful, one at a time stream processing. It is really optimized for high performance because Flink was built from the get-go as a stream processor, not built as a batch processor, then was extended to also do streaming. And also its fault tolerance mechanism, so the way that Flink handles errors. I'm going to try to give you an overview of these, or how these are achieved, hopefully without going into too much detail. So starting off with the Flink API stack, Flink has this kind of layered API style that gives you different trade-offs of how expressive you can make your programs or how easy Flink is to use. And at a higher level, you have APIs like Flink SQL or PyFlink or the table API that are closer to like this relational way of thinking about data. And these APIs really allow you to express problems in a very concise way. And again, you can just relegate all the operational heavy lifting to Flink. And as you progress down, maybe Flink starts being a bit more complex to use, but you also get more and more control over the programs you are building and also how they are executed. So when you reach the core building blocks of Flink, so when you're really working on top of just raw events, state, and time, basically the sky is the limit. You can do whatever you want. And I hope that for you now, it's a bit straightforward to really map the categories of use cases that we talked about before and how they map into this API stack. So you would use something like Flink SQL, PyFlink, or the table API to implement some use cases from streaming analytics and machine learning. And when you want to do this more classical core stateful stream processing use cases that you really want to max out, you can just use the data stream API or something like process functions with this, which is like this very low level construct that you have in Flink. So at the core of this, independent of what you choose or what API you are building your Flink applications with, it all boils down to the very simple model that we started with. So you have your code, and this could be, in this case, it's data stream API code, just a little piece of Java, but it could also be like a Python program, and it could be a bunch of SQL queries. And the premise is always the same, right? Your code just really defines where are your events coming from. So you have your source, what transformations you are applying, you are applying to your data, and then where to sync those results. And in this case, what I'm doing, for instance, is I am consuming temperature sensor measurements from Kafka. So I add my Kafka source, and then I'm applying some transformations. What I'm doing here first is just converting or just mapping my original temperature values from Fahrenheit to Celsius. Then I want to key my events by my sensor ID so that then I can apply an average over a window of 5 seconds. And in the end, I'm just sending these results down to an Elasticsearch sync. And this is how you as a developer create a very basic streaming application. And then what Flink then does is that it simply just translates your code into a streaming data flow that is just a graph of operators that kind of represent what you want to perform on your data. And because we are talking about distributed systems, we are talking about really very high volumes of data, and everything is moving really fast, you don't really want to just process these things in one machine, right? You want to be able to scale your computation and to distribute your load. So what Flink does is that it takes care of just distributing your topology into a parallel data flow that you can really run distributed on multiple machines. And the great thing is that if you have a stateful operator, like we have our window operator, that is just kind of remembering events so that after every 5 seconds, you can just trigger your aggregation on top of this data. What Flink does is that it automatically also reshards your state. So even if you are running your job and you stop your job and you want to start it again, but with a different parallelism, Flink just takes care of resharding and rerouting your state and scaling it as part of the scaling of the rest of the application. So you don't have to take care of these things by yourself. Okay, so in our case, what we have, like I said, is a window operator, which is stateful. And this means that we are writing the events that arrive in this window of time into Flink state. So that when the time comes to trigger this window, we can just apply this average computation to the whole content of your state. And the good thing about how Flink does state management is that it stores your state always locally in the instance that is processing your data. So it does this either in memory on the JVM heap or spills it to disk on embedded key value store that is called RocksDB. And this means that access for your computations is super fast, and it's either at in-memory or disk speed. And the amount of state you can keep for each operator really is only limited by the heap space that you have or by the disk size of your cluster. And like I mentioned before, one of the most challenging things and also one of the most important things when you are doing this kind of stateful processing and these stateful operations is to really make sure that your state can survive any kind of failure. So it might be you have a worker that goes down, or maybe you have some downtime due to something else, some operation that you need to do. And Flink should be able to really make your state fault tolerant and recover from that and produce correct and consistent results independently of whatever happened in between. So the way that Flink makes sure that this happens is using something that is called checkpointing. So Flink takes periodic snapshots of your state, and it stores it in some persistent storage like S3 or HDFS. And it's not only storing just the state, like in our case, not only the Windows state, but it's also storing the position of your input stream when you are, like the position at which you are consuming when this checkpoint happened. So in this case, exactly because we are using Kafka as a source, it's a durable and replayable source. Part of the snapshot is also your position, the position where you are reading the stream. And Flink persists this into its own state. It doesn't depend on Kafka keeping track of the offsets that it's consuming. So when something goes wrong, like I said, like if a worker goes down, your job gets canceled, Flink is able to automatically recover from the latest, the most recent checkpoint that you have in this persistent storage. So it does, when it comes back, then it basically recovers all your embedded states. So it recovers all your Windows state in this case. And it also resets the position in your input stream. And what this allows you to do is that it allows you to just automatically continue or move on with your processing like nothing ever happened. And it also gives you the highest level of consistency that you can have, which is exactly once consistency guarantees. And exactly once here doesn't mean that your events are only processed once. It just means that no matter how many times your events are produced, they will only affect your application state once. And with Kafka, it always depends on the sync also that you are using. But if you're using Kafka to Kafka, you can also achieve exactly once end-to-end. And this fault tolerance mechanism also extends to something that is called save points. And in theory, it's kind of the same thing as a checkpoint, but this is manually triggered and controlled by you. So basically, you can at any point just explicitly trigger a snapshot for something, just to have like a planned and manual backup. So this allows you to handle things like downtime situations, like when you want to upgrade the Flink version that you are running, or even when you want to migrate to a completely new cluster without losing any state, or when you just want to make changes, you want to stop your job and make changes like change the parallelism. And what save points allows you to do is just like to get a consistent snapshot of when you stopped your job, and then just restart from that point, like nothing happened with whatever changes you did. And the last thing that I want to mention that is also very important to the core of Flink is this concept of time and how Flink handles time. So Flink has support for two different, oversimplifying it, has support for two different types of time, event time and processing time. And we always find that the easiest way to really explain the difference between these two is to refer to Star Wars movies. So in Star Wars, the order in which the movies were released isn't really the order in which the events are happening in your plot. So your event time would be when these events really happened in reality. And then processing time would be when these movies were released. And in Flink, like choosing one or the other mostly affects the latency with which you can process your events, and also the correctness that you choose for your results. So if you want to process events exactly in the order that they happened in the real world, you can configure Flink to use event time. This is the time that is embedded in the records when they are produced. And what this enables you is to have deterministic results. No matter how many times or how you process your streams, you always get the same results. And Flink also gives you some tooling to reason about out-of-order events or late events, and it really allows you to choose the trade-off that you are willing to make of how much latency you put into your pipeline, but also how complete or how sure of how complete your results are. And then if you don't really care about having really accurate results, you can just configure Flink to use processing time, which is the system time of the machine that is processing the data. But then the downside is that you get non-deterministic results. So every time you reprocess your data, it will have a different timestamp, and so the results will never be the same. Okay, finally, to recap, I just want to summarize a bit what I've been blabbering about. So what makes Flink different to other stream processors is really this combination of things. It gives you very flexible APIs that allow you to trade off how easy it is to use Flink and how expressive you can get with Flink. And this allows you to cover a very wide range of use cases, but also allows you to open Flink to a lot of different levels of skill. So you don't have to be a Java or a Scala programmer to use Flink. And the second characteristic that is very particular to Flink is that everything is designed around state. So state is the first class citizen of your application always. And it has like this rich time semantics that I was just explaining a bit ago that allows you always to do things like reprocess historical data consistently, or to really not give up on how correct and how complete your results can be. You can choose whatever trade-off fits your use case. And about performance, like I said before, Flink is really built to operate with high performance. This is done with things like I explained before. So you have local state access, so all your computations can be done at in-memory speed. And the way that the network stack is built in Flink really allows you to achieve high throughput with very low latency. And the last point is also, of course, related to state and fault tolerance. And Flink just ensures that your applications are fault tolerant always and can handle failures with very high or the highest delivery guarantees. Okay, so I hope that this gave you a bit of a good overview of what Flink is, what people are using Flink for, and what under the hood really makes it so powerful as a stream processing engine. And I've put here, I've collected a couple of resources that you can use to get started with Flink. Like I said, you don't need to be a Java or a Scala engineer. Don't have to be a data engineer. You can follow along some hands-on tutorials in Java or Scala, but you can also complete like a completely zero code Flink SQL walkthrough. And if you're into Python, you can also just use PyFlink, and you can even do it with using interactive notebooks, which is a pretty common tool for data scientists. If you want to learn more about Flink, just visit flink.apache.org. I really encourage you to subscribe to the user mailing list, especially if you are getting started. You can always ask any question there. Anyone from the community will get back to you within a couple of hours, or you can just shoot us a question on Stack Overflow with the Apache Flink tag, and someone will also get back to you. And yeah, to wrap it up, you can also follow us on Twitter. And we actually have a release coming up really soon. So if you want to stay on top of what's happening in Flink or what's happening with the Flink community, yeah, just follow us on Twitter. Yeah, another way that you can get started with Flink, if you want to do Flink on Kubernetes, you can use the WeAreDevelopers platform community edition. It's completely free to use forever. You have unlimited application size. You can even use it for a commercial use. So this is really a kind of plug and play tool. So it saves you, especially if you are getting started, it saves you a lot of operational overhead and really having to go down to the weeds of how to deploy Flink and that kind of detail. Okay, thank you so much. This was actually my first ever Flink talk, so I really appreciate if you would reach out to me and give me feedback about how you felt about the talk, if it was too high level, if you learned something, if it was terrible. Yeah, I think I'll get some questions now.
Nice. Thank you very much for giving us this talk. Super engaging. As you can see, we have a bunch of questions already. And I'm going to start by putting them up on the screen, and so everybody can read them and you know what you're answering. So the first question is, since you said that core feature is stream processing, how good Flink is in batch processing and ETL jobs in comparison to other solutions? Also, please include your experience to answer.
Yeah, I mean, unfortunately, I can't really include my experience because when I was working as a data warehouse engineer, I was always using these very legacy systems, non-scalable kind of stuff. So I never actually used Flink. I never actually got the pleasure to use Flink during my job. But what I can tell you is that Flink is becoming slowly but steadily, actually not that slowly, like also a very, very good batch processor is kind of coming to the same point as streaming. And this is really like in Flink SQL, for instance, you already have unified operators for batch and streaming. And there are two optimizers. So it's like if you're doing batch loads, Flink really is then using optimizer to run it as batch and not the same optimizer as it used for streaming. So I can't really give you like any particular indicators of how good it is right now, but yeah, at least it is also pretty optimized to do batch processing. This was a big chunk of the contributions that Alibaba did were actually also in this direction of making batch really strong also in Flink.
Thank you very much. I hope it's answered. Our next question is, what is Apache Kafka required for when using Flink? What does Kafka help with?
Kafka is not really required to when you're doing anything with Flink, really. I just mentioned it because it's a very common very common piece of software that people use just as their source of truth. Like, so this is basically just something that you either consume data from or that you output data to. It's very common that you have pipelines that are consuming from Kafka with Flink and then outputting maybe to Kafka again.
Thank you. Then we have another question from Grigor. Kafka is powerful event source, but what other event source adapters you have out of the box?
So out of the box, you have support for, I think all the common event sources, especially when you're talking about things like message buses. You have out of the box support, really good integration actually with Apache Pulsar as well. Also with Kinesis, you have support out of the box, and yeah, basically anything that is not natively supported in Flink, it's also very easy to just write your custom event source. So yeah, you should check out on the website. There is you can see the Flink ecosystem, or in the connector area, you can really have an idea of what Flink supports natively.
Good. Then we have quite a long question from Tabi. Do you need to provide your cluster size beforehand, or does Flink manage horizontal scaling in some other way? I've also looked at using Apache Beam on top of Flink. Are there any advantages, performance, or otherwise gained from staying in Flink versus using a portable stream process runner like Beam? Maybe
Okay.
let's one by one.
So regarding your cluster size, as far as I know, this is currently you have to define this before you deploy your job. But you can at any point just change this. And if you're running Flink in a containerized environment, for instance, you can always just spin up new containers. About Apache Beam on top of Flink, I think that most people, or at least the use cases that I've seen people using Beam on Flink were mostly for two things. One was for the unified APIs that it gives you. So like it allows you to process batch and streaming. And like I was saying in a question before, Flink is very close to also being able to, or to also being like a truly unified across all the API stack. And the other use case was really to use it or for multi-language support. So a lot of people were using Beam with a Flink runner so that they could run Python jobs. And also, like I told you before, now Flink also has a Python API. But if you want to use Flink with Go or some other language that Beam supports out of the box, then it's still a very valid use case that you use Beam. And these are the main things that I'm aware of as to why people were using Beam with Flink.
Good. I hope Pabe is satisfied with the answer and can look deeper into it as well. Then we have a question about the APIs. Also, APIs are, as you said, very flexible. Can you make example of very custom event data processing? For example, some worker in machine learning pipeline.
Yeah, one thing that I forgot to mention is that you can actually mix and match. I think it was in the slides. You can mix and match all of the APIs. So you can do things like use Python UDFs on the Flink SQL API and stuff like that. So about your question, can you make very custom event data? When I talk about really custom things, is things like watermarks, so like how you keep track of progress of time in your system, or when you want to have something like side outputs and that kind of things. I don't think I can give you any specific machine learning pipeline example, but you can check out, there's a talk from Lyft about just enabling machine learning organization-wide at Lyft. So I'm sure that there they explore like some really edgy, customizable use case.
Thank you. So that's a good tip to have another resources that you can look into. And another question from Gregor, very active. Thank you for the questions. It always helps to keep the conversation. Do you plan to provide all features for Python API as you have for GFM languages?
At least for now. I mean, we are launching Flink 1.11 soon. I think Python was only introduced in Flink 1.9. And as of now, it is really built kind of on top of the table API. So for now, it is kind of, I mean, the table API is something that you can use with JVM languages. So ideally, Python just extends everything that is underneath in there. So yeah, I think it also really depends, because the ways in which you would use PyFlink maybe are not the same. It would be something, I guess the operators would always be a bit more oriented towards these analytics use cases, and there are other things that maybe are more important, like you want to integrate with libraries like pandas, or you really want to be able to use Flink's machine learning libraries with PyFlink. And I think the priority is a bit more about usability. And yeah, it depends on what features you are asking about.
Good. And our I thought it was our last question, but let me just answer first the questions about the slide, as it always comes up. Where would the slides be available? So there will be a recording of everything available, of the whole session available on our YouTube, on WeAreDevelopers YouTube channel. And then Marta maybe can say if she's willing to, if she can share the slides separately later.
If you give me a second, I think they are already up on notice. Let me just check. Maybe I can already provide you the link to the slides.
That would be great. And, then we actually have just one question left. Is anyone using Flink in production with .NET Core? How do I get started?
No, Flink doesn't really have support for .NET. So I don't think you can get started unless Beam supports the Flink runner also with .NET. Yeah, I'm really sorry, but it's not. It's something that is just really not available currently. What you can use with Flink is really JVM languages or Python or SQL.
Thank you for the straight answer. So for everyone who is still here, Marta has put right now a link in the chat section for her slides, so you can already access them. And as I said, you can always go back to the recording. It will be available most likely in 2 days on our YouTube channel. Yeah, thank you everyone again. Thank you, Marta. We went through it very easy and smooth. Thank you very much for being so engaging, for the insightful presentation.
Thank you.